So who can tell me about electrochemistry? It's the measurement of electrical signals associated with systems that are incorporated into an electrochemical cell. What's an electrochemical cell? Anybody? You guys remember half reactions? So electrons are going to want to flow one way or the other, right, on one of these electrochemical cells. In each cell, we have a particular half reaction, and the direction of flow of electrons is going to be governed by those standard reduction potential. So whichever reaction is favored to receive the electrons is the way these electrons will flow. And in this case, we have electrons flowing here to the copper, right, to produce copper 2, or to take, react with copper 2 to produce copper. So, right? Wait, yeah. So the zinc is donating the electrons to the copper, basically. And these are two half reactions that are put together, and we have a salt bridge that allows for the flow of ions either way. But what we're interested in is this electric potential between the two, okay, or the electrical signal between the two. So in this case, we're measuring the current in I, or the current between the cells. And we can also measure the voltage, which is the potential difference between the cells. If we don't have any current, we can put like a voltmeter there, and that'll tell us which direction and how the strength of that direction for those electrons to flow. The current is the actual flow of electrons. So if we're just measuring the voltage, this is known as potentiometry, because we're measuring the potential between these two cells. So does that make sense, or these two half reactions? Voltammetry is we're going to measure the current. And then we can also have coulometry. What do you think we're measuring when we measure the coulometry? Yeah, so what's a coulomb a measure of unit? It's basically the charge. So coulometry, we measure the amount of charge that gets transferred from the other. So with potentiometric methods, measures the potential difference between two electrodes immersed in a solution with zero current. So that's important to remember, that potentiometric methods, we don't use current. We just measure where that current wants to flow from. We measure the potential difference, okay? So the electrodes and a solution make an electrochemical cell, and each electrode is characterized by some half cell reaction. In this case, we have, looks like a hydrogen half cell and an iron reacting half cell. And if we don't allow the current, we'll be able to measure, 0.41 volts is the difference between those two half cell reactions. So it's going to want to flow from the iron to the hydrogen. And half cell reactions, we've seen this in general chemistry, right? So we have all these half cell reactions, and it all has to do with how basically the electron affinity of these reactions, right? Increasing strength as you go down in the voltage or the reduction potentials. So potential is always measured against a fixed reference potential, and in this case, they typically give you these tables. They use the standard reference electrode, which is your hydrogen electrode, which is really not very practical for us in a lab to have one of these hydrogen electrodes set up. These are measured at equilibrium, and the activity is related to this molar concentration via this equation here. So what do we mean by activity? Like, what would be the difference between the activity and the concentration? Because you can have concentrations of ions that don't have activity, right? Because those ions aren't available to take part in this half cell reaction. So you always remember that when we're using potentiometric methods, we're measuring the activity of the ion, not the actual concentration. Typically, the concentration is going to be related to the activity, but some cases you might have ions that aren't available for this reaction. So remember, it's the activity, not the concentration per se. And this shows you a typical potentiometric cell where you're going to have some reference electrode right here, this is your silver chloride reference electrode. You have silver and silver chloride in solution with a potassium chloride solution, some sort of frit. And then this is your ion selective half cell, where again you have silver chloride inner electrolyte, and then some ion selective membrane that's going to interact with your sample and be able to the concentration of whatever ion this is selective for will cause a potential difference across the membrane. So it's important also to remember that with these potentiometric methods, that we're not actually taking ions out of the sample and going into the electrode. It's just measuring how they interact at the membrane, right? Does that make sense? People always get that confused. They think that this membrane takes up the sample and then it interacts in here, but no, it's just, it'll bind to the membrane and you'll generate a potential difference across this, which will alter the difference in potential between this one, because this one is there, it's always constant, versus this is will change based on the concentration you have in the sample and how much is interacting at the membrane. Does that make sense? Maybe? So, indicator electrode is chosen to respond to a specific analyte species. Reference electrode does not change. Again, only the potential difference between the indicator and the reference electrode is what changes. And that's because that indicator electrode is going to change based on how it interacts with what's in the sample. The indicator is just constant. It gives you like a reference point where you can measure the electrochemical potential of the cell. And you have this, that's going to be equal to the electropotential of the indicator, subtracted from the reference, and then this liquid junction on the cell, and that's like a constant also. So the only thing that really should be changing is this. So then we can relate this back to the activity of the ion that we're measuring in the solution in the sample. Does that make sense? So there's a number of different types of reference electrodes, and it's the half cell reactions that's used as a fixed reference for the measurement of the cell potentials. The standard one is the standard hydrogen electrode, which you won't see in a lab because it's very impractical to have the hydrogen gas, in a half cell with, reacting with, hydrogen ions and electrons. You will see these two a lot. Standard Coulometric electrode, which has mercury, and that goes from liquid mercury to ionized form of mercury, or the silver chloride electrode, where silver, gets reduced to silver metal. And in fact, this is what we have in our pH meters, and I've seen these before in pH meters too. So. And this is what they look like, right? This is the saturated calomel electrode, where you have these potassium chloride crystals. So that's what keeps this potassium chloride solution saturated. If it's, have the crystals there in a saturated solution. A lot of times when I first started working in a lab, I would see that in the pH meter, the crystals. I was like, oh, this is bad. This electrode's gone bad. But no, my boss would tell me, no, that's the way it's supposed to look. And that's because you have the crystals in there. So. And then you have the silver chloride, also contains a lot of potassium chloride. And those potassium chlorides there just to keep that always the same too. Then your indicator electrodes or your sensing electrodes should interact with the analyte of interest. So E indicator reflects the analyte's activity in solution and not other compounds. So it's ion selective. Are the electrodes that we use. They're ion selective electrodes, and it measures the potential that develops across the selective membrane. So you don't get current flowing through the membrane, it's potential across that membrane. The interaction between the membrane and the analyte will alter that potential. And I think the first one we look at is our pH meters, right? Oh, maybe not. This is just showing you concentration dependent calculations. But I'm not going to make you calculate the concentration. Well, I'll make you calculate concentrations in your lab, but not with the Nernst equation. But this is what I was talking about. The glass membrane electrodes are used for pH. So because the silicon oxide of the glass will be able to absorb hydrogen ions, right? Those hydrogen ions will alter the potential across the one side from the other. If you have a constant amount of cations on one side, that will react with the glass. The more hydrogen ions you have, you'll have more positive charge on the outside, which will change that potential difference. So most widely used for pH, pure silicon oxide, it's an insulator, so you gotta have some sodium oxide, calcium oxide, lithium oxide, or barium oxide added. And upon immersion, dry glass forms a hydrated layer. So that's why you always wanna keep those pH meter electrodes wet. If they dry out, you gotta let them sit there and regain this hydrated layer, which should take some time. If you take a dry one and try to measure the pH, it'll constantly be changing as it starts hydrating, right? And what happens is you get exchange between hydrogen and sodium occurs at that glass layer. So, yeah, you can also have liquid and polymer membrane electrodes. You have some water insoluble viscous solvent that has a dissolved ionophore. Hydrophobic organic ion exchanger and a neutral carrier, and this is your membrane that has the ion carrier. It'll bind, in this case, the cation, which changes the amount of charge you have across the membrane, basically. So that change in charge across the membrane is going to alter the electric potential of this half cell reaction compared to the reference, which will change the amount of voltage, the potential difference between the two, right? And typically, examples of these carriers, this is probably the most famous one, is valinomycin. Right? You heard of that? It's antibiotic, and it forms, it's a good way to get potassium to travel through membranes, right? It's an antibiotic. You can disrupt potassium currents with it because it'll coordinate potassium and it'll cross a membrane. But in our case, we have it in the membrane. You don't get the flow across the membrane, and it just binds the potassium. So it's very selective for potassium, and that's what we use in our potassium selective electrodes. And these are some others. So you have valinomycin. I can't read this or any of these. Sorry, that's from the other book too. Solid state membrane electrodes is where you can have a single crystal or pressed pellets of some salt that must have some degree of electrical conductivity, low solubility in the solvent that we'll be measuring, which is typically going to be aqueous. And the example, this is what we're going to use today, is a lanthanum fluoride doped with gold. So you have this crystal and it's pressed and it's on the bottom of our electrode. And it'll bind with fluoride, basically. Oh, and that's all I got for that. Gas sensing electrodes are a little bit different, and it's important to recognize the difference with the gas sensing electrodes. With gas sensing electrodes for potentiometric methods, what happens is we have a permeable membrane that will absorb a gas, and it's selective for the gas that it absorbs. In this case, we're looking at a carbon dioxide, electrode. So carbon dioxide will go across the gas selective membrane and react with the water that's in solution there. When it reacts with the water, it produces carbonic acid, which will dissociate into bicarbonate and hydrogen ions, altering the pH of this solution. And then you just use a regular glass electrode to measure the difference. The change in pH basically is related to the amount of carbon dioxide that is coming across the gas sensitive electrode. So this is the potentiometric electrode. Here is just a pH electrode. And we use a gas selective membrane to measure how much pH change we get outside of that membrane. Does that make sense? Same thing with an ammonia sensing electrode. You have a sample here with ammonia. The ammonia will travel across the ammonia selective membrane. That will react with the water to form ammonium, and rather than bringing the pH down, it's going to bring the pH up. based on ammonia concentration. Does that make sense? And this is another picture showing you that carbon dioxide electrode. Here's your gas membrane here, CO2 permeable membrane. The sample comes in, CO2 will go in here, change the pH, and then here we have, where is it? pH sensitive glass membrane here that measures the change in pH. That's based on the amount of carbon dioxide that goes there. So ion-specific electrodes carry use and interferences. So the sensing tips are fragile. I think one of the tips we have back there doesn't work, so we'll have to identify which one that is, unless I took it out of commission last semester, but I think somebody damaged that in the past. And before we go do that, I think we should rinse the inside, because with these fluoride electrodes, you leave them dry. And I'd like to rinse them with water before we add the buffer that goes in there. There's internal calibrators, and Nernst's equation is temperature dependent, right? So calibrations and samples should be done, under equal temperatures. So if you calibrate it and it's really cold in the lab, and then you're taking samples and the AC stops and heats up, because in there it'll heat up fast, but they kick us all out of there when that happens because we don't get ventilation through the hood. But it'll alter the values, the accuracy of your measurements. Some compartments or components can absorb to the surface of the electrode too, and they must be removed. So, salts and things. Voltammetric methods, you have actually apply the potential to the electrochemical cell, and the current that is generated results, the current that results is then measured. And it uses a 3-electrode configuration, rather with the potentiometric methods just uses 2 electrodes. With this, we have a working electrode, a reference electrode, and an auxiliary electrode. The potential is applied via a potentiostat, which is just like a power supply, basically, that can give you what potential you want to deliver. And forces changes to any electroactive species at the working electrode surface via electrolysis. So you can basically force electrolysis. And then the current that's required to sustain electrolysis provided by the auxiliary electrode. So you want to force that electrolysis and then sustain it. And voltammetry in unstirred stationary solutions is voltammetry. Flowing or stirred solution is hydrodynamic voltammetry. And you generate one of these known as a voltagram, right? And you have this limiting current that you can measure and determine, concentrations of your ions in solution that way, or species. And this is another picture showing you the same thing. And this shows you, if you don't stir it, the distances that you get that redox reaction occurring will slow down, because those ions, the oxidants and reduction, was going to have to get closer and closer to that electrode, right? You'll use them up. Increases as time goes on, you increase the diffusion distance away from that electrode. So that's why there's a difference between having a stirred solution and an unstirred solution. So amperometry is where you measure the current generated at a fixed potential by an electroactive analyte, and the potential set where the IL occurs, and the current measured is directly proportional to that analyte concentration. So, electrodes, working electrodes should be good electroconductors. They should be inert. You don't want them to react in these redox reactions. So typically they're platinum, gold, mercury, or some kind of glassy carbon. Auxiliary electrodes need to be conductive, and they're typically just a platinum wire. Reference electrodes are going to be your silver chloride or your saturated calomel electrode. So. And then your oxygen electrode is an example. So it's designed as a complete electrochemical cell. Current generated at the platinum electrodes directly proportional to the oxygen concentration. So what happens is the oxygen gets reduced to hydrogen peroxide, and that's caused by that electron transfer. And the current that you generate then can be measured, and it's directly proportional to the oxygen. And this is another picture showing you the same thing. So the oxygen will diffuse through. Under the voltage, the potential difference will drive these electrons to react with the water and the oxygen to produce hydrogen peroxide, or hydrogen hydroxide, right? So it's a Clark-style amperometric oxygen sensor. Anodic stripping is when you have what happens is you want to measure something that's really, really low in concentration. What you do is you concentrate it first on the anode. So this is useful when we're trying to measure heavy metal concentrations, because typically heavy metals are going to be really low concentrations in biological fluids. So you have to concentrate those first before you can measure how much is there. And what they do is the analyte is first deposited on the anode, and then it's removed from the anode by the application of increasing positive potentials, and the resulting current that you measure is related to the concentration of the analyte there. So that's how you measure things like lead or mercury in biological solutions, would be via anodic stripping voltammetry. Conductometry. So electrochemical technique to determine the quantity of an analyte present by measurement of its effects on the electrical conductivity of the mixture. And you have an alternating potentials used to prevent the polarization of the electrodes. Decrease in the solution resistance results in an increase in the conductance, and more currents passed between the electrodes then. The current's directly proportional to the solution conductance, and conductometry is frequently used to measure the volume fraction of erythrocytes in whole blood. Does that make sense? So the more erythrocytes you have, the less conductive that blood will be, because you have these large, membranous bubbles basically in that solution. So there's less electrolyte solution there to exchange that current. Does that make sense? Okay. Coulometric methods just measures the amount of electrical charge passed between the two electrodes in an electrochemical cell. And the amount of charge passing between the electrodes is directly proportional to the oxidation reduction of an electroactive substance at one of those electrodes. And it's used for the determination of chloride in serum or plasma. And these are basically like a titration type reaction where you titrate the chloride, and that the amount of electrons you used is directly correlated to the amount of chloride that was there. Does that make sense? And then we have our enzyme-based biosensors and amperometric detection. This is one that we've done before in the point-of-care testing lab. Works this way. So we put the glucose on a strip that contains an enzyme, and the substrate's glucose in the blood. The enzyme, they don't have it here, do they? Got it here. Right, so the glucose oxidase is in on the little strip that we use. There's glucose oxidase that will react with oxygen to form hydrogen peroxide. The hydrogen peroxide diffuses across the membrane, which will then generate, the current at that platinum electrode. You get that redox reaction at the platinum electrode. So the amount of glucose that reacts with the glucose oxidase is, tell you how much the more glucose you have, the more hydrogen peroxide you'll produce, meaning the more electrons you'll get at the platinum electrode, and the more current you'll read. Does that make sense? So this is a enzyme-based biosensor. And this is the same picture, basically, the different book. So glucose goes through the membrane, reacts with glucose oxidase to produce hydrogen peroxide. Hydrogen peroxide generates that current to produce oxygen, and we get the current. And this shows you the ammonium selective membrane again. And this is another enzyme related where you're measuring ammonium concentrations, or urea basically. You measure urea. Urease is in there, which creates ammonia and carbon dioxide. The ammonium diffuse across a membrane, generating that current in exchange for potassium. So. And then we also have these, and this isn't in your book either, the DNA biosensors. You have some sort of electrode with a capture probe that has a sequence that you want to be able to bind to. If you have bound sequences, you get oxidation of guanine on the target when you apply current to it, and that will tell you that reduction oxidation intercalation species causes the redox reaction at the electrode. And you can measure that generation of the current.